Welcome everybody. This is our content and data platforms at Vevo presentation. Today we're going to tell you a story about rebuilding and scaling some of our services from zero in a year. The very important part is in a year. I think we got a lot of stuff done in just 1 year with very little development resources. Just a little bit about us, in case you're wondering who the heck are these guys. My name is Miguel Alvarado. I am Vice President of Data and Analytics at Vevo. And this is...
hello, everybody. My name is Alan Zavari. I'm a senior engineer at Vevo Content Services. I'm a backend engineer and mostly do serverless stuff.
And there's our contact information. There's our social media information, as well as email address if you want to contact us at any given point in time. So this is what to expect from the session. We're going to talk a little bit about Vevo, for those of you who don't know what Vevo is. We're going to talk a little bit about engineering within Vevo. And then Alan is going to talk to you guys about content services at Vevo. We're going to go through what are content services, what it has taken to rebuild content services, and how Lambdas fit into this whole re-architecture picture. Then I'm going to talk a little bit about data services. Also, I'm going to talk about what data services are. I'm going to talk about building a whole data platform from scratch in about a year. And then we're going to also talk about how Kinesis fits into the data services picture and how it is kind of like the central nervous system for data within Vevo. So what is Vevo? So Vevo is the world's leading all-premium music, video, and entertainment platform. We do about 19 billion video views a month. That's a big number. This is worldwide throughout all of our properties, including our syndication partners as well. We deliver a personalized and curated experience that allows people to explore and discover music videos, original programming, because we produce our own original programming as well. Very little people know that, actually. And also live performances by artists that people love. We deliver these experiences in mobile, web, as well as connected televisions. So I want to talk a little about the scale of Vevo, so you can wrap your head around what our world looks like, more or less. So I already talked about our monthly video views. This slide is a little outdated, but it's more like 19 billion a month. On the first half of this year, we streamed about 900 million hours of video. That is 51% more from the previous year. So it's a big increase. And I don't have the numbers of how we're looking as we close the year, but I believe that we've gone up about 70% overall for the entire year, compared to the previous year. One interesting thing about videos, music videos that we found is that it's a much more social medium than audio. People tend to share music videos twice as much than they share audio tracks on social networks. We have reached about 25 million unique viewers a day. We have about 400 million unique viewers a month. To put it in contrast, the US population is about 340 million people. So it's a big audience that we're dealing with. Here's an interesting information piece. So if Rihanna was a TV show, that would be a little bit weird if she was like a TV show. Imagine you wake up one day, oh crap, I'm a TV show. Anyway, if Rihanna was a TV show, the week of the premiere for her video work, she would have come in number 2, right below the Oscars and right above The Walking Dead. So, those are big numbers. She had about 8.8 video views, 8.8 million video views in that week of the premiere. Another similar data point that just kind of illustrates how pervasive music video has become. So Justin Bieber, when he put out his Baby video, it took him about 4 years to reach 1 billion views. In contrast, fast forward to Adele's Hello release, it took her only 88 days to reach the same amount of views. So you can see how over time, music videos are becoming more and more popular. So Vevo has been going through this reinvention. Before 2015, this is how Vevo looked like. We had a very noisy, loud brand. It was a little bit confusing. It was very in your face. And so we've been transforming the entire company, the entire product. We've been redesigning all of our products, and that also includes our brand. So now we have a much more sober brand, and now we're all about putting our name to the side and putting the artists in the forefront. So let's talk a little bit about engineering at Vevo. There's kind of like two phases of engineering at Vevo. before the reinvention, engineering 1.0, and then post-reinvention, engineering 2.0. So our CTO, Alex Nunes, who joined Vevo last year, he's done a fantastic job at just kind of rebuilding the entire product and engineering organizations, along with Mark Hall, our head of product. So the old world looked like this. We had a hybrid hosting infrastructure. We used Rackspace and AWS together. We had these big, heavy mega services. And believe it or not, most of the code bases were in .NET. There was no continuous delivery, and there were no tests. And loads of technical debt. The technical debt came because the organization was very reactive. People were reacting to what the business wanted without proper planning and proper engineering practices. So now Vevo Engineering 2.0, this is what it looks like. We're 100% on AWS, and we're using Kubernetes as well. We use containers. Everything we run production is running in Docker containers. Now we have a microservices and nanoservices architecture. And now we have a heterogeneous environment. We support various languages. We don't believe in that one language is the best for everything. We have the philosophy that you just got to pick the best language for the problem that you have at hand. So the languages that we support today are Go, Scala, Java, and Node.js. Now we have proper continuous delivery systems and pipelines, so every little piece of code that we ever deploy goes through our continuous delivery pipelines. We have a more test-driven process. We also have a more behavior-driven process in place. We've rewritten most of our stacks. And yes, we're hiring, so if anything sounds interesting to you guys after this presentation, come talk to us. So now I'm going to pass it over to Alan.
Thank you. So during the course of this presentation, I'm going to refer to content services. So before we talk about them, let's see what content services is. So whenever you watch a music video, let's say Justin Bieber, Katy Perry, Taylor Swift, Adele, or your favorite artist, regardless of where you watch this, on your mobile phone, on your TV, on your computer, doesn't matter. And it doesn't matter if you watch it on YouTube or on Vevo. This has brought to you by content services. So what we do actually, we deliver video to the audience. So that's the responsibility of our team. And this includes some things like metadata, and video ingestion, video encoding, enriching metadata, publishing to different providers like YouTube, for example, and providing some APIs for other teams and other client platforms to use this metadata. And data.
All right, so I'm just going to define what data services are within Vevo real quick, so there's context. So the data services at Vevo are the collection of services and infrastructure that encompasses the Vevo data platform. There's kind of like two Uber goals or two Uber things that the data platform covers. One is it powers smart consumer experiences in the form of personalization and recommendations, but it also provides analytics to all of our business and product groups so we can make data-driven decisions. The data services team is composed by platform engineers as well as data scientists. Back to Alan.
Okay, so this part of this presentation is about content services and how we re-architected the old architecture. So I'm going to talk about what this old architecture was and compare it with the new architecture and tell you the story of how we migrated from the old one to the new one. So our old architecture actually was a giant monolithic service which was responsible for everything you can think of. Authentication, serving metadata, searching metadata, and playlists, even recommendation. They were all served from the same service. And you can imagine if something goes wrong with the service, all these things go down together, and that's bad. It was written in .NET and SQL Server, and you can see how it looked like, the simplified version of our old architecture. So as you can see, lots of arrows and dependencies are there, and components are tightly coupled, and they are dependent on each other. And also you can see there is a relational database as a central place. Everybody's kind of connected to that database, and they're all using the same thing, same database. And at the end of the day, we have artists and video, which provides API, metadata APIs for the clients to use them. And when I refer to metadata, let me explain what metadata is. So when you watch a video has some specification. For example, it has a title, it has a start date, it has a main artist, it has a genre. These are the things that we call them metadata. And so this was the old architecture, and this is how we created the new architecture. We tried to break that giant service into different microservices, which are independent. So we created different independent microservices who are not talking to each other directly. Instead, they're talking through their Kinesis stream. So every microservice has a Kinesis stream of its own, and it writes events to that stream. And if it wants something from other services, other microservices, it just consumes or listens to their stream and consume whatever they want. So it's kind of asynchronous. No direct API calls between microservices. And these streams are kind of real time. And also, every stream has its own JSON schema. So not everything can go on the stream, just a specific schema for every stream. And as you can imagine, this is very cost effective because of its nature of microservices. So every microservice has its own database, consume as much resources as they need. And because of that, we saved some money here. Also, these microservices are mostly serverless and created with Lambda and API gateway. So we save some dollars there as well. And we also created continuous delivery for this new architecture. So I'm going to show you how these components are working together. This is the overview of our new architecture. And as you can see, that the orange tiles are microservices that I'm talking about. And those horizontal lines, green and blue, are the streams. So every microservice pretty much talks to one or maybe more streams. One of these streams is their own stream, so they are owner of one stream at least. And they are communicating with the Kinesis streams. I'm not going to talk about every one of these services, but a general overview is that we ingest the video metadata passes to the stream, and another service just validates the metadata. Another service enriches metadata, for example, adds more information to this, which gathers from different resources, enriches it, and then publishes it another service. And so they do their own job as a kind of workflow-like system asynchronously. And the beginning of this new architecture, the entry point is those blue streams, artists and video raw. So, but as you can imagine, it was not very easy to create such architecture from that one. So it was challenging. One of the challenges was that the old system was in place and working in production. So we couldn't just turn it off. We needed to gradually switch to the new system from the old system. And this old system was evolving. And of course, you can never, even if it's 100% complete, you can't just switch to the new system over the night. It needs to be gradual. And one of the things that we didn't want to do was changing the old code base, the .NET code base. That was a big no-no for us. So we didn't want to touch the old code, and we wanted to kind of connect these two worlds somehow. Why? Because we wanted to test the new service. So the new architecture needed some live data. We needed somehow to read the data, live data from the old system and push it to the new system. So to do that, we introduced a project called Mexit, which was acting as a bridge between these two worlds. And it's basically a Lambda, and a set of Lambda to be accurate, and runs on a recurring basis, like a scheduled task every 5 minutes, and reads changes from the old system. So if metadata changes or if we have a new metadata, it queries from the old system. And if it detects any change, it writes it to the stream of the new architecture. So it reads from the old API, push it to the stream. That's what Mexit does. And it's also fault tolerant. So because of the nature of Lambda, maybe something happens. What if the Lambda doesn't run? So we can't afford to lose any metadata. So we wanted to make sure that we never lose anything. So we always keep track of the last successful timestamp and store it somewhere in DynamoDB. And next time, when the Lambda runs, we continue from that point on. So we always kind of guaranteed that we get the changes and we never lose anything. So the one interesting thing about this project Mexit is that the whole thing was done in 2 or 3 days. So it was very quick, and it's been working since then. This shows how Mexit connects the two worlds, the old architecture, and sends live production data to artists and video raw. So from that point, new architecture does its job, and old architecture is not aware of this Mexit thing, because Mexit connects to the old API just like another client, queries just like another client, and it's not aware of that. So we wanted to make sure that everything is working, so we needed to monitor this Lambda. And here is a dashboard that we used for monitoring this project. It's a Datadog dashboard, and gets its data directly from CloudWatch, Amazon CloudWatch. So the graph that you see on this dashboard, they are standard Lambda metrics like invocations, duration, if any error has happened, and things like that. This is pretty standard, and you need to watch these things. But we needed more. So we wanted to actually count how many new videos we just inserted into the system, how many artist changes we had, and things like that. So those 4 numbers that you see on top left of the screen are custom metrics. And they are coming directly from Lambda. It's kind of interesting to know how we get these numbers to Datadog. So in Lambda, we send these metrics, like counter, directly to CloudWatch as a custom metric. So you can see these things in CloudWatch in AWS dashboards as well. That works. But we also wanted to get them in Datadog as well, everything in one place. And we were able to pull those custom metrics from AWS CloudWatch into Datadog. So we can see everything together. And so Project Mexit was one example of Lambdas that we used to switch to new architecture. But it was not everything that we did with Lambda. So here I'm going to talk about different scenarios that we used Lambda for various reasons. For example, as a scheduled task, or as a database trigger, or user-facing services, completely front-facing services, and etc. other use cases. I'm going to talk about every one of these scenarios for a couple of minutes. The first one is scheduled tasks. So we had some use cases which we kind of used as a scheduled task, as a cron job with Lambdas. One of the first thing that we did was kind of updating Elasticsearch index. So we have an Elasticsearch index, and it has all artists and video metadata. And whenever something changes, of course, we need to update the index or rebuild the Elasticsearch index for the changes to show up in search. So to do that, we set up some Lambdas who listen to the changes of metadata and update Elasticsearch. This was one use case, and the other one was I just explained Project Mexit, which does the same thing, similar thing, but instead of updating Elasticsearch, sends it to the stream, Kinesis stream. Another interesting use case was using Lambdas for cache warming. To give you some background, so we use caching for almost everything. All metadata are cached. And in this case, we're talking about artist images. So images are cached, no exception. And cache has a TTL. So let's say it's 4 hours. So the image is in cache for 4 hours, and then it's not. It should be fetched from the origin. So that's OK for most of artists. We have like hundreds of thousands of artists. That's fine. But we wanted to make to keep these top artists warm in the cache. So we wanted them to be served from cache always. So we created a simple Lambda, which does a very simple job. Every 1 hour, it hits top 500 artist images. It's a GET request. It sends a GET request to top 500 artists, or you can say 500 API calls. It happens every hour. So with doing that, we were able to keep these 500 artists in the cache forever. And of course, it's because of performance improvement. Another example was, which we used scheduled tasks, was Project Releaser. So like I mentioned, every video metadata has a start date. So video might be ingested today, but it's not necessarily live today. It might go live next week. So every video has a start date, and that defines the premiere time. So we wanted to kind of notify some services that this is time. The video went live. It's released. So we created this service releaser that does polling. It checks video start date on a recurring basis again. If it's time, it just pushes some event to a stream to notify whoever is interested about new premieres. But there was a problem. So you might know Lambda has a limit for recurring tasks. It used to be 5 minutes, the minimum frequency, and it's now improved. It's 1 minute. But it was not something that we were looking for. You can imagine 1 minute is a long time. So when we say premiere goes live at 8 a.m., it's 8 a.m. sharp. It can be 8:01 or 7:59. So we wanted to do this checking, this polling every 5 seconds. And Lambda doesn't support 5 seconds. So we did a trick. What we did, we created a long-running Lambda, let's say 5 minutes. So a Lambda with 5-minute timeout. And inside that, we start a timer. So I'm going to show you some piece of code here, which tells you how this works. So there is a main timer inside the Lambda, which runs every 5 seconds. It's a pretty simple code, but it does the job. So every 5 seconds, it runs, and it processes the videos that they need to be published or whatever it's going to doing. And it just works every 5 minutes. And this happens again and again and again until we reach the 5-minute Lambda timeout. Maybe 1 second, 1 second before that 5-minute timeout, we stop the timer. So before Lambda expires, we stop the timer, and it's safe for the Lambda to die. So Lambda dies, and immediately another Lambda starts, and same thing happens again and again. So with this mechanism, we were able to do this kind of improve the Lambda frequency to 5 seconds. Other scenarios was using Lambdas as database triggers. So we mainly use these kind of projects for not changing the source code. So we needed to do something without changing the source code. And this feature enabled us to do so. The very first Lambda that we created at Vevo was this first item that you can see here. So a little bit of background story. We are storing user likes into a DynamoDB database. So whenever you like something, for example, user X likes artist Y. This is a record in DynamoDB, and we store it. And we wanted to kind of capture these likes and send it to a stream. In other words, we wanted to stream enable the like services, which was not a stream enabled. So what we did, we just listened to, created a Lambda, which listens to database changes, create, modify, and delete, and turn it to an event to a stream. It was maybe 20, 30 lines of code, very simple, but it does the job. And similar use case was capturing user likes and send it to Redshift or S3 for further analysis. That was, again, another Lambda which we did and did the job. But one of the interesting things that we did with database triggers was for replication. So cross-account DynamoDB replication. This was something that we were told we should do for all projects, and we did it with the Lambda. So for your information, we have different environments, staging, dev, and production. And every environment is hosted in a separate AWS account. So the accounts are different. And for this project, we wanted to have a copy of production data in staging environment. So we tried different methods, for example, nightly backup and hourly backup and restore and things like that. So the problem was that they were different accounts. They are not in the same account, staging table and production table. And we end up doing this, which was a Lambda again. So how it works, it just listens to the changes on production database, and whenever something happens, whatever it is, it's a create, update, or delete, it just writes it directly to the other table in staging account, which of course we need some cross-account IAM role, need some setup. But once you do this setup, the Lambda just works. And this Lambda is hosted, as you can see, in production account. So it's in production account and creates a copy and replica of whatever is happening in this account into staging. And we were able to do it, and it works in real time, as you can imagine. It's much better than nightly backups and things like that. And so it's not very specific to Vevo. You might want to do the same thing. I'm going to share the source code for this in a blog post maybe later. And next slide is, so far, whatever I said was using Lambda as a kind of helper or as a tool, DevOps things, and, but not a service. But we actually created a service, a full feature service, microservice as well. What's called Project Souza. It's a user-facing service, and as you can see, it does link shortening. So you're all familiar with Bitly. This is something like that. We have a domain called Vivoli, which takes care of Vevo short links. So every link shortener needs to create a short link, and it needs to expand it. And this project does actually a bit more. It captures the event, social events. I'll give you an example. And all these things were done with separate lambdas. So this is what happens. You create a short link when you want to share something. And we attach those events to the link. For example, it knows that you are a user on iOS device and you're trying to share something to be shared on Twitter. And then later somebody clicks on that, but it turns out that the link was copied to Facebook, so the actual referrer was Facebook. So we track these kind of things. Because of that, I can call it a smart link shortening service. So it's very good to have such thing as a black box, which does its job, and it's kind of independent microservice. But we were actually able to do something better. We broke it into 3 nanoservices because of Lambda, which means for every single feature, we had a Lambda. For link shortening, there is 1 Lambda. For expanding, which means whenever somebody clicks on a link, that's another Lambda. And for capturing the events, again, another Lambda. So if, for example, for some reason, shorten goes down, you can't create a new short link, but you can still, links always work. So links should always work. And expand, because expand is working. And for this project, we use Lambda, API Gateway, and DynamoDB. I'm going to show you just some initial design diagrams for this project and how we used Lambda. So the first one, this slide, is showing how user creates a short link. As you can see, client just asks the system to create a short link by a GET request. The request passes API Gateway, and that triggers Lambda 1. Lambda 1 creates a short link, but before that, it uses Lambda 3 for authentication to see if the user is authenticated or not. And if it's OK, then it just creates a short link and stores it in the database. At the same time, Lambda 0 is working and capturing the events as a database trigger and sends it to the Kinesis stream for other consumers. So this is how we create a short link. And the other diagram is kind of similar, but for expanding a short link. So this is what happens when you click on a Vevo short link. You click on a link, it goes to API Gateway, and then Lambda 2. Lambda 2 queries the database for that key, and it finds the full URL with all parameters, and it sends it back to the user. At the same time, the events is also captured with Lambda 0. As you can see, there is no Lambda 1 for authentication because not everyone can create a short link, but everyone should be able to click on a short link. So it's open. And you might think that it's a very simple service, which it is, and get some traffic, true. But there is a caveat here. Because of the premieres that I mentioned before, we were expecting huge traffic increase at the time of premieres. So for example, something goes live at 8 a.m., and we see a lot of clicks from different places all around the world at the same time, concurrently. Because this is what they do. So for example, Sia the Greatest video, one of the last thing I remember, last hits. So she tweeted this short link on her own Twitter. You can imagine millions of people can see that tweet and will click on that at the same time. So we expect huge traffic. And this was a concern for us to see how Lambda reacts in these cases. And this is what happens. So at 8 a.m., these specific day. This is a 24-hour graph. We had a premiere at 8 a.m. And you can see that regular traffic has increased 80 times. This is a huge change. And not every service can tolerate such a huge spike. But fortunately, this system, which is Lambda-based, it tolerated it. And nothing went wrong. And we didn't lose any user clicks or any video watch. So everybody was happy. To be honest, actually, we didn't notice that this happened. I was looking at Datadog, and I noticed, wow, what is this spike? And it was, wow, so it works. And this kind of, assured us this, that we can rely on Lambda for high traffic, even spiky traffic services. So before that point, we knew that, OK, Lambda is a good thing, and it works, and it's very fast, rapid application development, and blah, blah, blah. But after that, we kind of look at it in a different way. So it's more reliable. Other use cases. We use Lambda. One of the things was we wanted to hit different external providers. So we had some data payload, and we wanted to send it to different providers. And we created Lambda for every single provider. So what Lambda does, it just massages the data and shapes it in the form that the provider requires it. And it just makes an API call. And without Lambda, it was kind of difficult to do so. But we easily created different Lambdas for different providers. This was part of Project Dartmouth, which Miguel is going to talk about. And one interesting thing that we did recently, this is actually the last thing that we did, was Slackbot, Slack integration. To give you some history about this project, not everybody is an engineer in Vevo, of course. So we have content operation team. We have business side of the Vevo who are working with the content. One of the things that they want to do is purging the cache on demand. Sometimes, for some reason, they want to purge the cache for a specific video. For example, they want to update the view count of that video immediately for different reasons. So we have a cache busting mechanism, and it works, but they want to do their own thing. So they said, we want this to be purged from the cache, fresh data to serve to the user. And we have a Slack channel actually called view count purge something. And so they ask us, they ask engineering, could you please remove cache, clear cache for this video? And then somebody answers them and do it for them. And it's been like that for a long time. And we thought, maybe we can do better. So we created this Slack bot, which is actually a slash command. I'm sure you've used slash commands. We created a slash purge. So what they do, they just type slash purge and the video ID in the same Slack channel that they used to ask us. So nowadays, they just say slash purge video ISRC, which is the video ID. And that goes to Slack. And Slack is calling the endpoint. That is a just REST endpoint, as you can see with API Gateway and Lambda. And that calls different APIs for cache, for purging the cache in different layers. So we don't have one cache. We have different layers of caching, and we need multiple API calls to do that. So with that project, they kind of became so happy that they can do it themselves in Slack, not even opening a browser or something like that. So that was very cool. With this, we're coming to the end of content services section. I hand it over to Miguel, who is going to tell us about how they built data services. Miguel?
Thank you, Alan. That was great. It's pretty incredible to think that all this new architecture was built, again, in 1 year. And I mean, how many developers? Like not even 5?
Yeah.
So it's a very small team. So I think that by reusing a lot of existing a lot of existing technology, you can get very far very fast. So let's talk about building data services from scratch. So when I joined Vevo, which was in November of last year, this is what the data/analytics world looked like. So there was no data team in engineering. There was no Vevo Data platform. We had no first-party data, no data science, and therefore no personalization, no recommendations. The company had been using a third-party product called Comscore DAX for analytics. There was no continuous delivery. So this is more or less high-level what it looked like from a technology perspective. This slide is important because it highlights that we have 15+ client platforms that we need to support, including all the different connected televisions, all mobile devices, et cetera, et cetera. So that's a lot of client platforms. So that became problematic because there had to be custom instrumentation for analytics on every platform, and then ensuring that they were consistent across the board was very, very hard. So it was a little bit of a mess. You can see that Comscore DAX is there. Then there was this process that would take aggregated data from Comscore and put into Redshift because it was just easier to manipulate and deal with the data within Redshift. It was really hard to get data out of Comscore DAX. And then there were some Tableau and also Looker visualizations. I don't have the Looker box in there. They say that when you're behind something, instead of playing catch-up game, you should figure out a way to jump ahead and leapfrog and see how you can get ahead. So because we were so behind data science and we didn't have any data scientists when I joined, we started thinking, well, how can we get ahead? How do we deal with this problem? So we started Project Dartmouth, and it was all about looking at third-party machine learning providers and see if we could use one to help us get our recommendations in a better state. So we looked at a few dozen companies, and out of a few dozen companies, we picked top 5. I can't disclose the names of these companies, but the top 5 machine learning companies that we found. And the thing is that it became really hard to figure out which company to use, because if you look at the specs of each one of these companies, they all look great on paper. They all look fantastic on paper. We had meetings with all these people. They're all very smart. So we started thinking, well, how can we make a decision with this? So we decided to put these guys to test against each other in production, because in production and real user data is the best way to make a data-driven decision. So we said, all right, so why don't you guys power our feed in iOS? The feed is the first thing that you see when you open up the app. It's just a list of recommended videos. And we want you guys to do real-time event collection. So we'll send you data in real time, and we'll need you guys to give us real-time recommendations. So whenever we request recommendations, you should give us responses in real time. And we picked one KPI for them to improve because we had to come up with something. So we said, hey, look, why don't you improve swipes to clicks ratio? Maybe it wasn't the best KPI to pick, but it was something to go with. So we built this little POC of event collection, and this was done in about 2 weeks. So in 2 weeks, we're able to bring online all 5 machine learning companies against our production environment. So this allowed us to also test some hypotheses that we had around event collection and a client SDK. So what we did is very quickly wrapped up this Endo SDK that we had been working on, which is basically an abstraction for all the client platforms on top of our event collection service. This is so that you can reuse the same event collection code in all the different client platforms. We wrote this SDK in JavaScript, and for native platforms, we use React Native so that this JavaScript can be interpreted in platforms like Android and iOS. It's a little bit of a hacky thing, but it actually works pretty well. Then we built a event collector service within those 2 weeks as well. This was done in Scala and Spray. And then we started pushing all of our events in real time to Kinesis. One thing that is not showing there is also, we were ingesting all the like events. And then we used Lambda as kind of an event router, a data router, to send the data to all these different machine learning providers in close to real time. And then we tweaked our feed service so that it would get recommendations from all these providers instead of the code that it had before that. So what we did, we segmented our audience in a very, very easy way. We just literally did mod 5, right? And then that gave us buckets, and then we put people in different buckets, which is a very, very primitive way to segment your audience. But we needed to do this very, very fast. So that was a way to do it. This is what the current data services architecture looks like. There's a lot going on there. I'm not going to go into every single thing, but I'm going to walk you through some of these things one by one. So again, talked about the cross-platform SDK that we have. That's turned out to be incredibly helpful. It gives us more consistency across events, across platforms. Also allows us to do some passive eventing. In other words, events that the client developers don't have to trigger themselves, but we can just deal with them within the SDK itself. And now our event collector is the most important piece of technology that we have out there, because without event collection, then nothing else matters. So this thing has to be super reliable, super fast, and up and running all the time. So we have Kinesis at the heart of our data nervous system. Like Alan was saying earlier, we have all these services producing data and then all these other services consuming data. Because we're the data and analytics team, we like to hog all the data, so we consume data from everybody and we bring it into our environment. Alan talked a little bit about this, but I'm going to go a little deeper into this. So, we wanted this environment where data is democratized and can be shared across all services, between all services. But we had to have a way to give it structure so it wasn't just like, craziness. So we had to come up with this service-to-service contract methodology. We decided to go with JSON because it's a lot easier to deal with in general. We looked at other technologies like Avro and Protobufs, and JSON turned out to be the selection. I think, honestly, any one of these technologies would have worked fine. But to reach consensus across organization, we picked JSON. So we decided that all entities that are going to write to Kinesis stream must have a schema. You can't send data to Kinesis and Vevo if you don't have a schema associated with this data. And there's kind of two methodologies that you can use. You can either send full payloads with the entire entity that is being created or modified, or you can send a message saying, hey, there's a new entity or there's a newly modified entity. Go find the payload over here. And it could be against the API of that service producing the data. And we made a kind of a rule that the data has to be pushed to Kinesis at the moment of creation or at the moment of modification, so we have a close to real-time system. So we have a central repository for schemas. We debated about this a little bit, but we decided that all schemas should go into a central repo, so that way we have visibility as to what new entities are coming through. That's a very simple sample schema that I put in there just so you get a better idea. That's the schema that supports the like event. So whenever you like something, an artist, for instance, there's a like event that goes with it. So that schema contains some metadata about the user and the entity that the user is trying to like. So that's data collection, that's event collection. Now, as far as data processing and analytics, we use currently, and this is going to change over time, but currently we use Spark for most of our data processing. We use Spark for real-time analytics. Most of the data that we generate, most of the metrics we calculate, don't have to do it in real time. We don't have to do that in real time. It's really just play counts and completion rates that we calculate in real time. We also use Spark for batch processing. So we have these periodic ETL jobs that run, and that's also based on Spark. And we're also using Spark for some machine learning, mainly to train models. There's some experimentation happening right now with the team using TensorFlow and Spark. All the Spark work that we do is with EMR. We decided to not go ahead and create our own Spark clusters. It's a lot easier to just manage through EMR. Plus, it's very easy. If something bad happens, you can just tear down the cluster, bring it back up, and it's no problem. So it's a lot easier to manage. And then we use S3 as our long-term storage place. So all of the data that we collect and generate goes into S3. And then we use Redshift for analytics. So after our ETL processes run and we generate metrics and we kind of spread the data into a dimensional model, then we put all of that into our analytics warehouse, which is Redshift. And then all the data is consumed from there by people outside of our team. So people consume data via Tableau, via Looker, and just SQL. It's actually quite fascinating because we've been teaching our product managers to write SQL. And they've been very excited, and they've become incredibly productive because now they can go ahead and do their own analysis and not depend on a centralized BI team. So one of the big goals that we had when we started all of this was to truly democratize data within Vevo, make it accessible to everybody without needing a centralized group to manage it for them. Now, that said, when we once we know that something needs to be upgraded as like a source of truth when it comes to data, then we'll create a looker visualization for it. So we'll create a dashboard, and there's kind of this section that we're calling the official looker dashboard section. And you know that if you're looking at a report from there, it's been fully vetted, fully QA, and that's the source of truth. But before that, you have to go through a lot of experimentation. So kind of like a recap, right? So we have data collection on one side, on the right side here. You see that everything goes through our event collector. You can see that there's some data being processed in real time there by Spark, being consumed from the Kinesis stream. We have this thing that we call the event publisher, which then pushes some of this data into this user behavior Aurora database. This Aurora database exists because we feed consumer experiences. So of course, we can't do that from Redshift. We can't do that from S3. So Aurora scales really, really, really well. So we decided to use Aurora for the front-facing services. So you see a bunch of front-facing services there, which mainly serve data that comes from Aurora. You can see the feed service there that I talked about earlier. There's a recommendation service that powers the feed and people recommendations as well. You can see that on the batch side of things over there, we have Spark with Airflow for ETL. Then we have Spark below for machine learning as well. You see the picture that I showed earlier where we have our BI tools that people use to interact with the data. Then everything above is stuff outside of our domain. So we see the third-party services that we interact with, and then all the other Vevo services that generate data that then we consume. So this turned out to be a pretty, even though there's a lot of boxes, a lot of errors, actually a pretty sweet architecture. It's pretty flexible. I mean, it's allowed us to move things around in many different ways. And this will continue to evolve, of course. So now let's talk about the lessons learned.
Yep.
Want to go?
Okay, lessons. So Lambda is great, but it's not all cupcakes and rainbows. So one of the things that we experienced very first days was that we need a framework. You can't just deploy Lambdas manually. If you do so, you can, of course, but it will turn to a mess quickly, trust me. So you always need a framework with Lambdas, and we used Serverless, which is a pretty cool framework, and we are happy with that. I recommend to use it if you're using Lambda. We also were able to integrate this serverless framework with our CI/CD framework. Another thing was throttled invocations. You might be aware of that there is a limit for concurrent runs on Lambda. It's by default 100. So 100 Lambdas can run at the same time. The next one just fails, gets throttled. And it's per account, it's not per Lambda. So you should always monitor that thing to make sure that you don't get throttled. And if this happens, it's an easy fix. You just ask Amazon to increase your limit. And this is what we did. And the other thing was the famous cold start issue. For those who are not aware of this thing, Lambda, when it runs for the first time, it takes some startup time. And next time, it just is fast. It runs the code. But for the first time, it's kind of slow. So if you're using Lambda behind a user-facing service, the first request might get a timeout, which is not good. So we fixed this issue with keeping the Lambda warm. So just setting a 5-minute scheduled call on the same Lambda helped. So it keeps it warm always and never experienced the cold start issue. Other things was, as we explained, standardize what goes on the stream, which helps a lot. And having a central place for all the stream schemas, that's also helpful. Because let's say you have a new hire and you give it a task, give him or her a task to consume this stream, consume the data events from this stream. All he or she needs to do is just go into that repo and having known the stream name, just find the schema for that stream, and then they know what to expect as an event for that stream. It's very helpful. And we did the same thing for error messages. Having same central place for all error messages from all services was very helpful. And other lessons?
So these are some of the lessons that we learned on the data side. I mean, you've probably heard this many, many times, but I mean, it's something I keep relearning over and over again in my career. Don't try to boil the ocean all at once. As you saw, we started small with the event collection system, and then we started moving to data processing versus trying to build a little bit of everything at the same time. This is something we learned with Project Dartmouth. Use real user data to make decisions. I mean, it was so... without Project Dartmouth, we probably would have picked the wrong machine learning provider. Maybe not, who knows? But it would have been like at luck. So always look at real user data. Reuse as much technology versus build. I mean, especially in the world we live now with all the services that Amazon provides, for instance. You know, there's so much to reuse, so don't try to build things yourself. And then if you're serious about analytics and data, because there's so much infrastructure already in place, build your own platform. I mean, nowadays, it's not as hard as it used to be. I'm not saying that it's easy either, but I mean, it's possible. I mean, you saw like all the stuff that we built in 1 year, and that was a small team. That was a 4-person development team that built the data platform in 1 year. So there's a lot that if you have the right people, you have the right infrastructure, you're using the right cloud technology, you can do a lot. And I believe that's it. Thank you very much.
If there is any question, feel free to use the mics.
If there are any questions, there's some mics there, so feel free to just reach a mic.
And please don't forget to do the evaluation. We appreciate it.